Welcome back. Take a seat and grab a hot drink like my special Easter chocolate chai. Today we're going to talk about unfolds, which are the partner of crimes of folds. They are different, yet you can't help but think that they're siblings. So a fold, if you recall from last time, it takes some data type A and it follows the natural grooves of the data type and peels it layer by layer, transforming it into some other data type. An unfold is going to do nearly the opposite. It's going to take any data type and bring it to a specific data type. So rather than being centered as in the type of the input, we're centered in the type of the output. And what an unfold is going to do is do this interpreting our input as our output in the most natural way possible, which is saying we're going to, whatever input we have, our unfold is going to tell us which parts of the input are going to become each onion layer of the output. So we're going to follow the natural structure of the output rather than the natural structure of the input. I'm going to put down some examples for folds just to recap ourselves on what they are and actually write these folds as unfolds. So a fold on lists, it replaces all the constructors that make up the list. It replaces the empty list and it replaces all the conses. But it keeps the shape of the expression tree. So fold L, E cons, it's going to replace the empty list with E. And it's going to replace all the conses in the list with this cons. We're going to say. And of course, we need to replace the rest of the list recursively. So the second argument to the cons is actually the remaining fold. Okay, so an example is to find the length of a list. To find the length of the list, you might say, okay, the empty list is going to have length 0. And for a non-empty list, well, here's what we want to express. We want to say the cons is going to be a thing that takes in the non-empty list. No, not x-axis. It's going to be a thing that takes in the x and the result of our fold and gives us 1 plus the result. That's going to say the length of our list is going to be 1 plus the length of the tail of the list. The result here is going to be the length of the tail of the list, the result of the fold. Okay. And the sum of a list, we could write that as fold L, the sum of 0, sum of the empty list is 0, and the sum of non-empty list, well, we're going to replace all the conses with pluses. Okay. So now let's talk about an unfold two natural numbers. I'm going to start with the definition. Unfold two natural numbers, unfold n. It's going to take two arguments, z and p. And also x, which is the input. What it's going to do is z is going to be a thing that outputs true or false. And here it's going to say, if zx is true, then we're going to output 0. Otherwise, we're going to output the successor of the unfold. But this time, instead of x, we're going to have px. This is what unfold n is. And what this does is it looks at the definition of a natural number as either being 0 or being the successor of a nat. And it's trying to interpret our input as either one of these. So the z is going to decide, are we going left or are we going right? And if we're going left, we're just going to output 0, because 0 takes no inputs. And if we go to the right, then, okay, we still have work to do. Since although we have a successor on the outer layer, on the inside we have nat, we have another natural number. So we have to keep on interpreting we have to keep on interpreting what's inside this onion. And to keep on interpreting, we use unfold n again. So you could see the similarities, how s nat becomes s of unfold of blah, 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 blah. And the px comes in because we're not going to be interpreting the exact same input again. Once we've interpreted a layer of the onion, we actually change the input. It's like we've taken a piece out of the input, so we could keep on taking new information. And that's what the px is for. Another way, a visual way I like to think about it, is the input x is some blob, and our zp are going to tell us how to interpret that blob as a natural number. And in the first case, where we have zx is true, the whole blob, our interpreter, our translator, our unfold, is saying, okay, well, this blob is just 0. In the second case, the blob is not really 0. Actually, we're saying that, okay, the blob's not 0. It's going to be in the form successor of natural number. But what it's going to do is output successor of the remaining of the unfold. And it's going to take a piece of the input and make that the successor. And it's going to take the other piece of the input, the px, and it's going to make that the input to our new unfold. So it's like we're cutting away a piece of the blob, and we're using the remaining blob for the rest of our interpretation in recursive style. Okay, so let's go back and see how we could write length and sum as unfolds to natural numbers rather than unfolds from lists. And before that, I'm going to introduce two helper functions. So I'm going to say 0 is going to take in a natural number, and if it's 0, it's going to give us true. And in every other case, it's going to be false. And I'm going to make a function pred, which is a -1 function for the natural numbers. It's only going to be defined on non-zero numbers, and it's going to say, okay, if we have pred of successor of something, we're going to return that something. Okay, so length as an unfold to natural numbers, we're gonna say that the length is 0 when we see the empty list. That's gonna be, I'm gonna call that null. Null returns true if we have an empty list and false otherwise. And here, we're going to, our predecessor function is going to be the tail of the list. So what this length is gonna do is in our blob diagram, we're gonna have something like the P is gonna be the tail of the list. And so our output is gonna give us one plus the length of the tail of the list. So when we're thinking about an unfold n, we're looking through the list and looking for in what situation are we adding 1 to our output. And with length, we're adding 1 to the output for each for each element in the input. So this is really natural. It looks nicer, actually, I think, than the fold version. With sum, the story is a bit different. So sum could also be written as an unfold n. And we're going to say, okay, the sum is 0 when we have an empty list again. But our predecessor, we're going to have to do a bit more work. So I'll call it P, where P is only going to work on non-empty lists. And P of xx's is going to have two cases. If x is not 0, then we're going to take one off of x and then return the rest of and return the list back. Let's say we either have 0x or we have otherwise. In the otherwise case, we're going to return x minus 1 constant to x's. So it's like in our sum, we've added 1 to our sum. So now our input is going to be, the remaining thing we have to sum over is going to be, is going to have the first element subtracted by 1. Or rather than x minus 1, maybe what I mean is pred x. It's the same thing, but with the way I define natural numbers, we haven't really defined minus yet, so it's a bit clearer if I use pred. Okay, in the case of 0x, so we look at the first element. This doesn't contribute anything to the sum. So we're going to have to look for the thing that contributes from the tail of the list. So I'm actually going to do that recursively. I'm going to say, in that case, our answer is going to come from peeling 1 off the tail of the list. Okay, so this is, while it's nice that we could write it as an unfold, it's quite different and less elegant compared to the fold version. Not only that, this one really relies on the structure of a natural number. We have to be able to peel off the inputs one by one, whereas this sum would work for anything that supported addition. So here we could see that for length, the unfold way could be seen as more natural, whereas for sum, the fold is seen as more natural. So if we flip between these two ways of thinking, we could think about our programs really naturally. Okay, so now let's talk about unfolding two lists. So unfold L is going to take in 3 inputs, N, H, and T. It's going to say, if nx is true, then we're going to get the empty list. Otherwise, we're going to get hx const onto unfold everything else, but applied to tx instead. Okay, so let's remember what the list data type looked like. So the list data type was either empty or it was something const onto a list. So our unfold is interpreting our input as these. So the N stands for null. It's saying, is our input interpreted as null? If it is, then we output the empty list. If not, then we have a non-empty list. And just like with the natural numbers, we're going to have to think, okay, how are we going to interpret the inputs to this non-empty list? Well, we could interpret something as the head with hx, standing for head. And we also need to interpret the tail of the list. Well, to interpret the tail of the list, we have to use unfold again, because unfold L is the function for interpreting lists. And again, we peel off parts of the data by applying the unfold to tx, which stands for tail x instead of just x. So in a blob diagram, in the case nx being true, it's going to say, okay, this blob goes to empty list. In the case of nx being false, it's going to say, okay, part of the list is going to become the head. And part of the list is going to become the tail. So it's like we peel off a bit as the head and we reinterpret the remaining blob as the tail. The T is going to tell us what is the remaining blob. H is going to tell us what is the head of the blob. Let's think about some examples. One I like is the ones function. So ones n is going to take a natural number and give us a bunch of ones. Actually, n ones. So this is going to be an unfold from natural numbers to lists. We're going to say ones is going to be equal to unfold L of, if we had, so we need to say when do we have the empty list? And we're going to have the empty list, and we have 0. And we're going to say when do we have when we have a non-empty list, what's going to become the head? Well, it's just going to be a 1. So I'm going to say const 1. And what's going to become the tail? I'm going to say pred. So what this is saying is, when we have a non-empty list, the head of our list is going to be 1. And the tail of our list is going to be, well, a list of ones of length n minus 1. Okay, so that's nice. And the next one I was thinking about is, I forgot, so let me check. We're going to be thinking about mapf. So mapf, if you remember, is a function that took a list of numbers and then applied f to each of them. And actually we could write this as an unfold as well. So mapf is going to be unfold L of, okay, we're going to interpret the input as an empty list when we have an empty list. The head of our list is going to be applying f to the head of our list, of our input. And the tail of our list, of our input is just going to be the output. I mean, it's just going to be the tail of the input. So what this is saying is, if we had a blob that was represented a non-empty list, we're going to have f of head x as the front of our list. So this composition means doing head and then doing f. And we're going to cons that onto the unfold of the tail of our list. So you can see that this is going to give us what mapf should give us. We're going to apply f to each thing in the list in turn. If you look at ones and mapf, you might remember, or you might have a creeping suspicion that we could have written these as folds from lists as well. Actually, not quite folds from lists, but the first one is a fold from natural numbers. The second one is a fold from list to itself. So yes, we could have. But these two ways of thinking about these two functions are quite different from the fold versions. And that's something for you to think about. Is it more natural to think of these as folds or unfolds? And what are the advantages of doing them in either way? Do they run? Do they have the same running time, or is actually one version faster than another? Here's a cooler example. Not saying the other ones weren't cool, but this one's cooler. So I'm going to define a function m to n that gives us a list of natural numbers from m to n. And that's going to be if m is less than or equal to n. And it's going to give us the empty list otherwise. So I'm going to write this as an unfold 2 lists. And in unfold 2 lists, we're going to be building this output from the head. So the first thing we're going to want to put in the list is the m, and then we want to put in the m plus 1, ... and we want to put in the n. So we want to be applying an unfold to m. We're going to be wanting to be changing this first input to the function as we construct the list. What I mean more precisely is that m to n is an unfold 2 list where we know we have the empty list when m is greater than n. And the head of our list is going to be id, which stands for identity. And what id does is it takes the input and does nothing. So the head of our list is going to be just m. And the tail is going to be the successor of m. We're going to apply the whole thing to m. So what this is saying is that a blob, where m is less than or equal to n, we're going to say, okay, the head is just going to be m, the tail is going to be the successor of m, and our new list is going to be m const onto the unfold of the successor of m. So actually sm to n. That's really nice. We have 2 arguments. We have this thing going on. It's great. And now you might be wondering, why do we want to write things as unfolds or folds? Usually, they seem a bit more abstract. And sure, it's nice that they're all one-liners, but there's also so much information. When we look at it, we're just like, huh? Maybe takes an extra few seconds to figure out what's going on, compared to a direct recursive definition. Well, there are a few reasons for investing into thinking about folds and unfolds. First is that they let us do lovely algebra, I quote. One thing we do in functional programming is we could specify a program. We could write a version of a program and then use algebra and use laws between the functions we've used to simplify the program or to make the program more complicated, usually so that the program runs faster. And with recursive functions, they take multiple lines, and so they could be very messy to use when we're trying to prove things or we're trying to do these simplifications to speed things up. But if we wrote things as folds and unfolds, we're capturing a pattern across a family of functions, and we could derive laws about folds and unfolds to make simplifying them much faster. And the second reason is that folds and unfolds, they give us such a nice way of understanding algorithms and functions. Once we see that actually a bunch of these algorithms all look like folds, it's very easy to understand. You could look at something and go, oh, that's a fold, that's a fold, that's a fold. Since it's a fold, it must have this shape. It has this shape, so it must be a fold. So it must have a feeling like this. It must have a running time that feels like this, and so on. It lets us save a lot of work rather than having to understand a similar shape over and over and over again. And to aid in the algebra, there are a couple of facts. The first, I'm going to call them identity laws. So if we do fold natural numbers and we replace 0 with 0 and we replace successor with successor, that's the same as doing nothing, which is the identity. If we tried to do a fold on lists and we replaced empty list with empty list and the cons with cons, that's also doing nothing. If we if we do an unfold to natural numbers, and we say, okay, from natural numbers, we say, okay, our input's 0 when it's 0. And the predecessor is just going to be a predecessor that's doing nothing as well. And with unfold lists, if we say, okay, our list is empty when it's empty, and the head of our list is going to be the head, and the tail of the list is going to be tail, that's going to do nothing as well. So actually, the identity function could be written as folds and unfolds. So this would be something like, if we were calculating and we saw one of these shapes, we could immediately go, oh yeah, this is doing nothing. It's like having a 1, where a times 1 is equal to a for all a. Or having a 0, where it's like a plus 0 is equal to 0 for all. It's equal to a for all a. These make our algebra more complete, gives us more tools to work with. So, as a challenge to you, why can't we write this function double, which is fold nat of 0 and successor compose successor? Why can't we write this double as an unfold from natural numbers to natural numbers? And second, when can we write a fold as an unfold? And third, can we write a factorial function that looks like a fold followed by an unfold? What I mean is, so the factorial is gonna, n factorial is gonna give us n times n minus 1 times dot 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 times 1. And we write a factorial function that does this. It takes n to the list n minus 1 dot 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 1, and then it products that list to give us n factorial. So this first step, it's going to be unfolding our input into a list. And then the second step is going to be folding the list into our output via a product, which is a kind of fold. Can we write a factorial function like this? So writing it as, first we go to the list world, then we come back to the numbers world. Okay. I'll take a break now and have some hot drink, and I'll see you next time.